Hi, everybody. Thank you very much for joining this seminar series once again. Today, we have the pleasure to have Jiabin Yu from Princeton University. Jiabin did his PhD at Penn State, then he moved to the University of Maryland, and now he's finally a Moore postdoctoral fellow at Princeton, working in close collaboration with Andrei Bellman. And today, he will talk us about Moiré fractional Chern insulator. So, please, Jiabin.
Right. Thank you. Thank you, Valerio, for the introduction. Thanks for the invitation. It's a great pleasure and honor for me to be here and talk about our recent work remotely. It will be about Moiré FCIs, and this is the outline of my talk. First, I will start with the introduction that provides the necessary background information, and then I will talk about two classes of system, bilayer MOT2 and pentalayer graphene-hBN superlattices, where FCI were experimentally observed last year. Starting with the introduction, starting from basics, band theory is one of the most successful theories in physics, it is a theory of the material properties, especially electronic properties. In this theory, we explored the lattice structure, which allows us to study the system as each individual block momentum. And the block momentum does not live in continuous space. It lives in the infinite continuous space. It lives on a circle in 1D, torus in 2D, and higher dimensional generalizations of torus in higher dimensions. And the energy is just functions of the block momentum for band structure. If the Fermi level is in the band gap, it would be an insulator like diamond. If the Fermi energy crosses certain band, it would be a metal like gold. So these are the classic band theory. But this discussion only uses the energies, and we also have the eigenstate, which is called block states. In the last several decades, the band theory experienced a paradigm shift centered around the topology of the block state, which is called band topology. So just briefly introduce what band topology is. So it is defined for insulators, or more generally the insulating parts of the system. For simplicity, let us consider a two-band system where we only have one band that is occupied. So for this one specific occupied band, the block state at each block momentum is just like a vector. So as the block momentum goes over the brane zone, the vectors can form a vector field. You can have different winding numbers. In 1D, the winding number is just like the winding numbers for loops and twisted strips and so on. In certain cases, in 2D, we have a special winding number called Chern number. And different insulators can have different winding numbers. And these winding numbers are like topological invariants of them, and they indicate the different topology of them. And often we refer to like insulators with non-zero topological invariance as topological insulators, and insulator with zero topological invariance as trivial insulators. And if you go from a trivial insulator to a topological insulator, you must go through a band gap closing. The non-trivial band topology is not just a mathematical concept. It can lead to interesting physical phenomena. Let us take a 2D insulator with Chern number 1 as an example. The non-zero Chern number can lead to anomalous gapless mode on the edge. And this mode is anomalous because it cannot be realized in pure 1D system. And it can lead to quantized Hall resistance or Hall conductance. Basically, if you thread a current along X and vary the voltage across Y, you can get this quantized value of Hall resistance of H over E square. And this phenomena was first discovered, as we probably all know, more than 40 years ago in the integral quantum Hall effect, where these different plateaus correspond to different quantized value of the Hall resistance, which come from different integer values of the Chern number. And later, people predicted and then realized that the zero magnetic field analog of integral quantum Hall effect, which is called Chern insulator, or in short CI, or quantum anomalous Hall effect. The key idea is to replace magnetic field which is required for integer quantum Hall effect by spontaneous magnetization, so that we can have quantized Hall plateau at zero magnetic field. So beyond this interesting phenomena, there are other reasons for people to care about non-trivial band topology. Basically, conceptually provides a principle to classify physical matter beyond the conventional symmetry-based paradigm. Like in conventional paradigm, superconductors and ferromagnets are distinguished by their different symmetry breaking, but symmetry breaking cannot distinguish different plateaus in the quantum Hall effect, because their difference is not the key differences on in symmetries, but in topology. And people have used this principle to predict thousands of topological materials. And on the application side, integer quantum Hall effect can help measure fundamental units like kilogram, thanks to its precise quantization. And in theory, non-trivial band topology can allow setups that holds Majorana zero modes, which can be used for topological quantum computing. So this is a brief review of the band topology at a single particle level. And recent years, there have been increasing amount of study on the combination of band topology and interaction. So there are two major types of interactions in solids. One is electron-electron Coulomb interaction, the other one electron-phonon coupling. In this work, I will focus on the electron Coulomb interaction, where I'll show that I'll talk about that the combination of non-trivial band topology of this interaction can lead to exotic physical matter like fractional Chern insulator. So to discuss fractional Chern insulator, let me first discuss more about integer quantum Hall effect. It can be given by a 2D electron gas under applied magnetic field, and this is the Hamiltonian for the system. P is the momentum, and A is the vector field, whose curl is the magnetic field, and M is the effective mass. So this Hamiltonian can lead to Lambda levels, which are exactly flat bands that carry Chern number 1 for each band. And if we fully fill new Lambda levels, we would have new chiral-anomalous edge modes, and each of them carry charge minus E. And this edge mode would lead to quantized Hall plateau, as mentioned before. And this discussion requires no interaction. But in experiments, if the magnetic field is large enough, we not only see a plateau at integer filling, 1, 2, 3, 4, but also see plateau at fractional filling. And this is called fractional quantum Hall effect. So the explanation of this fractional plateau must involve Coulomb interaction. To see that, let us take 1/3 as an example. If we neglect Coulomb interaction at single particle level, 1/3 just means that we fractionally fill the lowest Lambda level. At the single particle level, the Fermi energy just cuts the lowest energy level, and it will give us a matter, which is inconsistent with this plateau structure. So if we add Coulomb interaction back, we would naturally have a gapped bulk with anomalous edge mode, and this edge mode would carry fractional charge minus E over 3, which explains the quantized fractional value of the quantized Hall plateau. So this example already shows that the combination of interaction and non-trivial band topology can give us exotic physical matter, but this is 40 years old. What is new? The new thing is the zero magnetic field analog of this effect. So as I mentioned before, the zero magnetic field analog integer quantum Hall effect has been predicted and discovered, which is a Chern insulator. So the idea is to replace the fully filled Lambda levels by fully filled Chern bands, which come from the spontaneous magnetization. The zero magnetic field analog of fractional quantum Hall effect is the fractional Chern insulator. So basically, it's given by the combination of fractional field Chern bands and Coulomb interaction, as predicted by these people more than 10 years ago. After this initial theoretical proposal of fractional Chern insulator, or in short FCIs, people have been actively searching for this system in experiments. So the underlying motivation is twofold. First, if we can achieve FCI, it might help us achieve non-binary anyons beyond Majorana zero modes for topological quantum computing. So, and this is one setup, the proposed setup for this kind of non-binary anyons called parafermions, which are beyond Majorana zero modes. And it requires two fractional quantum Hall-like states and superconductivity proximity effect. If we use two fractional quantum Hall states, we would have really strong magnetic field, which would limit the choices for superconductors of this proximity effect, because magnetic field normally destroys superconductivity. But if we use FCIs, we don't need that strong magnetic field, which in principle might allow more choices for superconductors for this proximity effect. So this is one motivation. The other motivation is that FCIs that themselves are new physics matter, and the realization of them may help realize more exotic physics matter that have no analogs before. And I will discuss this more at the end of this section. So this is the motivation. And next question will be where to find FCIs. As I mentioned earlier, so fractional quantum Hall effect needs lambda levels and Coulomb interaction. Coulomb interaction is everywhere. It's not special at all. What is special is the lambda level. So basically what we need to do is to mimic lambda levels without magnetic field. And as mentioned before, lambda levels are exact flat band with non-zero Chern number. So we need to achieve at least nearly flat bands without magnetic field. Like it is really hard for us to achieve exactly flat band with non-zero Chern number without magnetic field. So at least a nearly flat band should be our goal. Okay. Next, I will argue why Moiré system is the natural place to look for these exactly flat bands with non-zero Chern number, or more generally, nearly flat bands with non-zero Chern number, or more generally nearly topological bands. Maybe I can stop here a little bit. If you have any question, you can ask me. If no question, I'll just continue. Good. I'll just continue. Yeah, if you have any questions, feel free to ask me and stop me. Okay, so why Moiré? We want to use Moiré to achieve nearly flat Chern bands or nearly flat topological bands. To understand that, let us first think about a normal lattice where this orange loop label the unit cell. Let us suppose this normal lattice has a cosine-like bands at low energy, and all other bands at high energy. And now, in theory, we are always allowed to double the unit cell, which would fold the lower part of the band back to the smaller brane zone. And if we further introduce a potential with this enlarged unit cell, we can open the gap at the band crossing due to the band folding. At the end, we will have two bands. And each of these bands would have roughly half of the bandwidth of the original bands. So basically, this tells us like if you double unit cell, you roughly half the bandwidth. And Moiré materials or twist materials are doing like folding the bands like hundreds of times. So now let us take two of these normal lattice and put one layer on top of the other and twist them with a small relative angle theta. And this twisting will give us a Moiré lattice with a lattice constant much larger than the normal lattice. And this large lattice constant means that the brane zone is extremely small. So it will fold the original bands hundreds of times. And normally we would have interlayer coupling or like relaxation or structure change at the Moiré scale. These two effects can bring us Moiré potential, which can open the gap at the band crossing due to band folding. And this gap opening at the band crossing is extremely similar to the band gap opening at the transition between the topological insulator and trivial insulator. So normally, some of the bands would be topological. So this is the intuition why like Moiré materials can naturally achieve nearly flat topological bands. Okay, and this happens in twisted MOT2, which consists of two layers of MOT2 and at a small like twist angle theta, which is around 3.7 degree in experiment. We would have spin doubly degenerate, nearly flat Moiré bands. And these Moiré bands, like the minimum bandwidth can be like 13 MeV. And the bands will carry non-zero Chern number in each spin subspace. So the idea is that if we can polarize the spin, we will have nearly flat Chern bands. And guided by this intuition, theoretical intuition, last year experimentalists made a big breakthrough realizing the fractional Chern insulators in twisted bilayer MOT2. So this is the main idea. At charge neutrality, the Fermi level is above all the Moiré bands. Okay. Now suppose let us take away 1 electron per Moiré unit cell. So at the single particle level, the Fermi energy would just cut the top pair of bands. And then since we have Coulomb interaction, it will open a correlated gap. As a result, a nu equals -1, which means we take away 1 electron per Moiré unit cell. We have an empty, nearly flat Chern bands with Chern number 1, and all occupied bands has Chern number -1. It is a Chern insulator, CI. Indeed, experimentally, they found CI, clear Hall plateau at inner value with 0 magnetic field. And if we further add back, in average 1/3 electron per Moiré unit cell, we would fill these nearly flat empty Chern bands by 1/3 fitting, and we go to fitting nu equals -2/3. And according to previous like theoretical or numerical intuition, we will have FCI. And indeed, in experiments, they found fractional quantized Hall resistance at fractional value with 0 magnetic field and fitting nu equals -2/3. So this and you may think these phenomena are like completely consistent with theoretical intuition, but this is not the whole story. There are various experimental puzzles that beyond the simple intuition. So let me summarize all the conclusive experimental signatures observed last year in twisted MOT2. So first, at nu equals -1, experiments find Chern insulators, CIs, at different angles, many different angles. And in this Sheldon's experiment, they found CIs at all these 3 angles. But at nu equals -2/3, FCIs do not happen at all angles. In the same Sheldon's experiment, FCIs occur at 3.7 degrees, but not for 3.52 and 3.9 degrees. And this was puzzling. And the remaining puzzles happened at nu equals -1/3 and -4/3. So at nu equals -1/3, like some sample shows magnetization, some sample do not. In these two figures, the red region are the magnetic phase, and white is non-magnetic, and you can clearly see that -1/3 is at the transition between magnetic and non-magnetic. And even if we polarize the spin, experimentalists polarize the spin at nu equals -1/3, they see no FCI. And at -4/3, again, no FCIs. And it's clearly non-magnetic in experiments. And the question for a series like us is whether we can capture all these phenomena, because only in this way we know the theory is reliable. So let me show you our results. Indeed, we can, with our current model, we indeed can capture all these phenomena. I nu equals -1, our Hartree-Fock calculation shows that CI happens at various angle. But our ED calculation at nu equals -2/3. Sorry, here the horizontal axis is the twist angle, and the vertical axis is the interaction strength, where epsilon is the dielectric constant. It cannot be exactly determined in experiments. That's why we choose it as a tuning parameter. At nu equals -2/3, we see that FCI at the fixed interaction strength, FCI do not happen at all angles. It has some optimal angles, which is consistent with experiments. Nu equals -1/3. We see the system is at the transition between red magnetic phase and blue non-magnetic phase when the system was FCI at -2/3. And even if you polarize spin, the system is largely not FCI. The competing phase is trivial charge density wave. And nu equals -4/3, like larger the system is non-magnetic, like indicated by this large blue region. And these results were used our parameters. And I would like to mention that before our work, there are other parameters that try to explain the phenomena. But if we use their parameters, we cannot capture all these phenomena. For example, if we use the like Tinsel and D-Shell's parameter, we can capture most of the phenomena, but at -1/3, we will see a large range of FCI when the spin is polarized, which is not that consistent with experiments. Okay, this is our results. Now let me tell you how we achieved this match. So first, we did reliable DFT calculation and reliable modeling. Our DFT calculation, like in our DFT calculation, we benchmarked 19 van der Waals exchange correlation functionals, and we used the best one for the calculation of the twist structure. And to get as many data as possible, we accelerated the calculation by machine learning. And when we build the model based on the DFT data, we not only match the band structures, but also match the charge density. Here, the left plot, black dots come from DFT calculation, and the red line are our modeling, and we can clearly see at least the low energy bands, the top two bands per valley. The match is quite good, and the right one is the comparison between the DFT charge density and the charge density from our model, and you can clearly also see that the match is quite good. So this is a single particle model, and more importantly, in our many-body calculation, Hartree-Fock or ED calculation, we not only include the lowest energy band, in like one band per valley, but also include the remote bands. And we found that the mixing between the lowest energy band and remote band is very important. For example, at nu equals -2/3, if we do not include band mixing, we cannot have this strap-like region of FCI. So basically, if we have only one band per valley, and we polarize spin, if FCI happens at a weak interaction, it would definitely happen at a strong interaction. That's why without band mixing, you will see FCI happens at many angles. And nu equals -1/3 and -4/3. As long as we turn on the band mixing, we can see a great enlargement of the blue non-magnetic region, making the results consistent with the experiments. And I would like to mention that the importance of band mixing were also studied in contemporary works by Yang Zhang's group and Emil's group. Okay, so these are the two important ingredients for our calculation. And now we have a reliable theory. The next step is to try to find more exotic phases based on FCIs. So the phase that we are looking at right now is the so-called fractional quantum spin Hall effect. And to introduce that, let me first review the integer quantum spin Hall effect, which do not require any interaction. It consists of a time reversal pair of two CIs, two chain insulators with opposite chain number and opposite spin. And experimental evidence of this phase is the even integer quantization of two-terminal resistance, like h over 2e squared is 2, which is even. Fractional quantum spin Hall effect consists of time reversal pair of the simplest version consists of time reversal pair of two FCIs with opposite spins. Its experimental evidence will be odd integer or fractional value quantization of two-terminal resistance. One experimental signature of this phase. And recently, like Phi and Jie found signatures of fractional quantum spin Hall effect and nu equals to -3 for a small angle sample of twisted bilayer MOT2, which is 2.1 degree. Previously, FCI were observed around 3.7 degrees. And we are currently working on the explanation of this phase. So this would conclude the part of the twisted MOT2. Any question?
Yeah, Jiabin, can you go back to one slide earlier? I wonder if this like optimization including this band mixing has anything to do with the flat quantum geometry that was discussed to stabilize fractional Chern insulator. Or it's
yeah.
So is there any connections?
So yeah, currently like we don't have very like precise theoretical understanding, but I have some intuition that I can share with you. Let's look at the -2/3, and the reason why you go to strong interaction and FCI disappear is that you see the remote band has opposite number at -1 as the lowest energy band. So when the interaction is very strong, the remote band will come into play and trivialize, even at trivialize the system. You can think about it like this. So if we have really strong interaction, like super strong interaction, these two bands just form an atomic limit. So like naively, it won't give us FCI, right? So this would be the effect of FCI. So sorry, the band mixing, current intuition.
So that's when your interaction projected to these two bands is comparable to your bandwidth. You say this.
Comparable to the gap between these two.
Yeah, to the band. Yeah. Okay.
Yeah. Yes.
Okay, I see.
Yeah.
Okay. Yeah. Thank you.
No problem. Okay, so this is the story on how much time do I left? Do I have like a lot of time? I guess, right?
Yeah, still roughly 20 minutes, I would say.
20 minutes?
Yeah.
Good. 20 minutes is enough. Okay, besides twisted body MOT2, there was another setup last year that showed FCIs, which is pentalayer graphene-hBN superlattices. So this is the setup. Pentalayer graphene is stacked in the rhombohedral way, and there's no twist in this 5-layer graphene. Okay, it's pristine 5-layer graphene, but it put on the hBN substrate, and the moiré happens between this 5-layer graphene pentalayer graphene with one substrate on one side. So the Moiré comes from two effects. First is the mismatch of the lattice constant between graphene and HBN. The second is a small twist angle, about 0.77 degrees. So experimentally, people found Longju's group found CI at nu equals 1 and FCI at various other fillings when they applied electric field to the sample. Okay, so the question is how to understand them. Start from the single particle. If we have no HBN, the pristine rhombohedral monolayer graphene has like a vertex at K point, and this vertex has order n, and n will be the layer of the graphene. And these low energy electrons are mainly localized at the top and bottom layer on opposite sublattices. Okay, so and if we include HBN, we would include it would generate Moiré potential. There are two effects. First is the hopping between the HBN and the carbon atoms on the lowest layer that closest to HBN. And I would like to mention that there are two configurations for the HBN stacking. One, like these two are related by the 100-degree rotation. Like Bn, like this, is we call it C equals 0. If we flip boron and nitrogen atom, that will be another configuration. We call it C equals 1. So besides the interlayer tunneling, there's another effect of the HBN, which is the relaxation. Since the boron wants electrons from carbon atom, if it is close to a carbon A atom, the interlayer distance will be smaller. So we can see like this boron atom like stack on carbon A atom, we call it AB region. For different stacking, we see that AB region always has the smallest interlayer distance. So these two effects together will give us the Moiré potential. And what does the Moiré potential do to the single particle band structure? It would open the gap and give us Chern bands. So this would be the pristine multilayer graphene band structure, which we have an n-fold winding. And if it further add the electric field perpendicular to the sample, it would make the valence band localized on the more localized on the bottom layer, and conduction band more localized on the top layer, and open a gap. And this gap opening would result like Chern number in half values in each value. And if we further include the Moiré potential from the HBN, it will be strongly it will strongly influence the valence band, because the valence band electron is closer to HBN to open a larger gap, and it would also include affect a conduction band in a weaker way to open a small gap. But this small gap opening can cause the Chern number of the lowest conduction band to be 5, or in general to be n, depending on the number of layers. Indeed, this is what we found in DFT calculation and modeling. Here, the gray dots are DFT calculation. The blue lines are our Moiré model. We found the Chern number 5 bands per spin per valley, but the gap between this lowest conduction band and the remote bands is very, very small. But experimentally, they don't see Chern number 5. They see Chern number 1. Why is that? Because we need to include interaction and do Hartree-Fock calculation. As I mentioned before, at a single particle level, Moiré has really weak effect on conduction band, but very strong effect on valence band. Since we consider electron doping from now we focus on conduction band, where at the single particle level, the Moiré effect is weak. But valence band, the occupied valence band, would give us a charged background like this at the Moiré scale. This charged background may affect in a correlated way the Hartree-Fock calculation or the many-body states. But this effect is different for different scheme we choose for interaction. And in our work, we use an average scheme, which has been widely used in twisted bilayer graphene, where we explicitly, like not explicitly, but the average scheme would automatically include a strong effect from the charged background. We also consider a charge neutrality scheme, which was also used in previous works on this system, where the charge background from the valence band are neglected. So in every scheme, the Moiré effect is quite important, even for conduction band, because the charge background from valence band is included. But for charge neutrality scheme, charge background from the valence band are neglected. So the Moiré effect is very little, very small. Let me first tell you what happened for average scheme. In average scheme, another subtlety here is that since we have multi-layer graphene, the 3D nature of the Coulomb interaction is actually important. So in our calculation, we would include the layer-dependent Coulomb interaction, not just pure 2D, like not just a 3D interaction like projected to the lattice, to the system. Okay, let me first show you the results on average scheme, Hartree-Fock result, and U = 1. So it does open the gap of the single particle band and give us a Chern 1 band. So more specifically, the gap closing and reopening happens mainly at K and K prime of the Moiré brane zone, and also at generic points. So the band mixing so here I show that the probability, the overlap of the lowest Hartree-Fock bands, the Chern 1 bands, with the single particle remote bands. You can see that at K and K prime, the mostly or completely come from the remote single particle bands, and on the edge of brane zone, there are some other points that also has strong mixing with remote bands, indicating some additional band inversion or band mixing. So basically at K and K prime, it changed Chern number by 2, and these additional generic points will change Chern number by 6, and eventually it gives us 1. Okay, so this is the average scheme. We see a large region of CI. In charge neutrality scheme, we also see a large region of CI based on the similar scheme, similar mechanism of changing Chern number. But what is the difference between this Chern insulator in average scheme and CI in the charge neutrality scheme? The difference is in the soft modes. Okay, let me explain what these two figures mean. This kappa, kappa is the strength of the Moiré potential. Kappa = 0 means that we completely shut down the Moiré potential. Kappa = 1 means that we include the realistic Moiré potential in the single particle model. Okay, for average scheme, we can see that at kappa = 0, the system is spontaneous, continuous symmetry, continuous transition breaking. So it will have 2 gapless ghost mode, which are the phonon modes. Because we have two direction. As we turn on the single particle Moiré potential, the gap of the ghost mode becomes larger and larger, and eventually they are not the lowest energy soft modes, and we have some other intervalley soft modes that are lowest, that are lower than them. So, but on the other hand, for the charge neutrality scheme, where the Moiré effect is weak, as when you turn on the single particle Moiré potential, the soft modes that come from the spontaneous breaking of continuous transition symmetry remains the lowest energy modes, even if we include the realistic single particle Moiré potential. So it means that for Chern neutrality scheme, the picture of this Chern insulator is roughly the same as spontaneous continuous transition breaking. And this was also found in previous work, and they call it anomalous Hall crystal. But in our calculation with average scheme, it's completely different from this picture because the soft modes that come from continuous transition breaking are not actually the lowest modes at when we include the realistic Moiré potential. In other words, if we starting from here, we increase the temperature, we first populate some other soft mode instead of this continuous lattice transition breaking soft modes. In other words, we tend to restore some other symmetries than the continuous translations. So we call it Moiré Chern insulator. So this is the point that the interaction scheme in this system is very important. Different interaction scheme can cause different results for at least for nu equals 1. This is one subtlety. Another subtlety is for the like before going to another subtlety, I want to mention that in our work we propose a way, experimental way, to distinguish Moiré CI and anomalous Hall crystal, or to distinguish these two interaction scheme. So for every scheme, if you change the stacking, like C equals 0, C equals 1, by flipping the hBN layer, we will see the Chern insulator disappears from, like, if we go from C equals 1 to C equals 0. And but this will not happen for the Chern neutrality scheme. So if experimentally people can really identify the stacking configuration, it is possible to distinguish these two interaction schemes. And I wanted to mention that in our calculation, and we see this kind of Chern 0 insulator close to Chern 0 insulator close to CI, and this kind of feature was also observed in experiment. Okay, so another subtlety beyond this interaction scheme is how can we get FCI? So of course, if we choose, if we do Hartree-Fock and nu equals 1, and pick out this Hartree-Fock band, project interaction on this Hartree-Fock band, and do ED calculation, we will naturally have FCIs, because this band is quite flat, it has non-zero Chern number. But this would show, like, this calculation will show FCIs at both 1/3 and 2/3, and the strengths of the FCIs and the gap of FCIs are quite similar. But in experiment, people only see 2/3 FCI, not 1/3 FCI. So if we use this method, there is a mismatch with experiment. So we are currently working on doing the ED calculation with 3 bands, not just the lowest Hartree-Fock bands. Basically, you can see that at single particle level, the lowest 3 bands are very close to each other. And the band mixing effect here is actually stronger than twisted MOT2. And we are also using not just the 2D interaction, we use the 3D interaction. And we also try to include the spin value fluctuation and to capture the precisely the experimental signatures. So this will be the end of my talk. I will, before concluding it, I would like to mention that in our paper, we not only studied 5 layer, we also studied like 3, 4, 6, 7 layers, and the previous discussion focused on one Moiré on one side, and if we make the other side of hBN also align a little bit, we can have the double encapsulated hBN devices. And in that case, at single particle level, we have more, it will have richer features for the Chern numbers. And that will be the end of my talk. And this is a result of big collaboration, and I would like to thank my collaborators. And thank you.
Thank you very much, Jiabin. Are there any questions? So in the meantime, I can go ahead and ask a question.
Sure.
So with your scheme, so the psi equals 0, psi equal to 1 has a huge importance. Could it be that there are spatial variation in the same sample between the two psi, or?
You mean psi equals 0? It's really hard to have psi equals 0 psi equals 1 in the same sample, because the difference between them is non-local. It's 100-degree rotation of the hBN.
Not even if I align the first layer of graphene with the hBN.
No, not even that. So it's really non-local difference. Yeah. So you need to flip N and B. You rotate the whole layer. Yeah. And I don't think you can have C1, C0 in the same sample. Yeah.
Other questions?
Right. Yeah, can you comment on the trends that you see with different number of layers?
Different number of layers. The
Yeah, for
trad.
the RoboHero case.
I mean, the trad is that, okay, first of all, at single particle level, the Chern number is different. Like basically, like the Chern number is just the layer number for the lowest conduction band. At Hartree-Fock level, we see the Chern number currently. Like we just did preliminary study of these other layers. We see it always reduced to Chern number 1. We don't really see other Chern numbers right now for the nu equals 1 for the conduction band. Currently, we are also working on the valence band, because Longju has some extra data on 4 layers, the valence band. Yeah, we cannot.
Yeah.
Currently, I cannot comment too much on that.
Yeah, I was especially wondering about the stability of these FCI phases. I think there's some older data by Andrea Young had experiments on tri-layers with the Moiré potential that didn't, at least in those early experiments, didn't see any FCIs. And so
yeah, to answer your question, we really need to like theoretically or numerically to resolve this question.
Yeah.
Like, from here, it's like FCI is so stable. We should just like if we just project to the lowest Hartree-Fock band, we will see FCI everywhere. But experimentally, we know FCI is not that stable. So we need to really sort out the way to do the 3-band ED, like to actually make more precise prediction for the trad. Currently, I don't have very precise.
Yeah, sure. Yeah, thanks.
No problem.
Okay. If there are no further questions, let's thank Jiabin